Tomorrow is my final exam in probability theory. I have been studying, but probably not as hard as I should be. Yesterday I studied pretty hard, and earlier than that, I just casually looked over at things. The test is about Brownian motion. Essentially, we have to go through this packet, skipping some things, skip other things not so much. And it's not the easiest concepts to learn. So you can read what a Brownian motion is here. We see that b of 0, it's a function, it's a family of functions that satisfy 4 properties here and there. You can pause the video and read them yourself. I just want to flip through this casually. But essentially, he gave us a list of things to cover from these notes. So we need to know what Brownian motion is. We need to know what a Gaussian process is, Markov process. We need to know the definition of total and bounded variation, but that's a familiar real analysis topic. A lot of this he told us we could skip. We don't need to know Ornstein-Uhlenbeck. Modulus of continuity, he said we could skip. Markovian structure, we do need to know this. There's Markov process, strong Markov process. I don't know about mutual independence or not, but I do know that he wants us to definitely know reflection principle because it's a very important topic. So these finer details I need to go through again. I didn't really study reflection principle yesterday because it takes a while to go through. But the picture kind of does most of the heavy lifting. If you know the picture, a lot of the finer details come along with it for free. Skip a lot of this. I don't think he covered it in class. He wants us to know absorbed Brownian motion, but that's not too hard to see or understand. We probably should have this part up here memorized. Embedding theorem, we don't need to know. Diffusion process, we don't need to know. Ramifications of martingale structures. So we need to understand the martingale structure. And then these examples are important. 11.3.1, 11.3.2. I did this yesterday, but I need to do it again. He did this in class, so it's probably important. This result here is probably important. And then this part here, he's probably going to ask us. So what is it? So what does this statement say? Sorry about that. Early on in this paper, or this packet of notes he gave us, he asked us to show that the expectation of tau A, or where tau is a stopping time, is equal to infinity. I understand that there's a lot of information prior to it that I'm not showing you, but early on in the packet, he asked us to show why this is true. And then he gave us a homework problem that asked us what is the expectation of tau A. and it was multiple choice, and one of the options was infinity. So I was a bit surprised to see that because in the packet, he just tells you the answer. So I go up to him, I was like, how come you just gave us the answer? And he's like, we don't actually need to evaluate the expectation if you just tell us that. And he says, no, but you should fill in the details yourself. Show why it's true when you have it. And then I read through the rest of his notes, and towards the end, towards the back of the page, he essentially shows us how to do it here. So I'm thinking that if he asks us to do this on a test, he's basically going to ask us to do all of this that you see here. Fill in all of this information, and then let B go toward infinity to show that this is necessarily true. I believe A here is negative. That's why it's negative A to make it positive, if B is tending toward infinity. So I'm going to go through that. A lot of this stuff over here, I think, is not going to be on the test. We can skip it. No moment generating function. Law of iterated logs is probably not going to be on there. And then just the exercises. So it's a bit much. I don't think the topics are... I think earlier I said they're not easy to understand, but I think if you go through it slow and just don't forget your martingale structures, you'll be fine. I just really got to understand the reflection principle. If I can do that, I'll be okay. And also, I want to make sure I do really well on this test because this is basically his last time teaching it, this course. I think he's been at the university for like 40 years or something. And he's the nicest, sweetest old man you'll ever meet. And I really wanted to work with him, but he says that he's really trying to retire. And I can probably say that of all the instructors I've had, if he's not my favorite, number one on the list, he's definitely in the top 3. So I was pretty upset to hear about him retiring and missing an opportunity to do research with him. But such is life, I guess. Now, I've been given 2 other final exams as take-homes. One from number theory and one from geometry, or problems of uniqueness. So they gave us these take-home tests a while back, and each test is one problem. And each problem is some famous result from that topic, either number theory or geometry. And I debated about whether or not showing you what the test is, because I'm technically showing you what a final exam is. But I've decided to do it anyway for 2 reasons. The first reason is I don't think the instructors really care, because the number theory guy told us basically how to solve the problem. Where there was one, actually it was the last day of class, we came in and he basically showed us how to do the easy problem from the test. He really gave us 2 problems, but he told us to pick one. And one of them is much easier than the other because you can just recreate a famous theorem that he gave us in class. So if you just adapt it a little bit, you'll have the solution. And even if we didn't do that, he basically showed us how to do it in class. So he gave us the answer, is what I'm saying. If he gave us the answer and the fact that this problem is famous, then I don't think he cares too much. And I'm not actually going to show you the solution. I am just going to show you what the theorem is that he wants us to prove. And I found the paper that he got it from. So this is the paper. It's about Goldbach's conjecture by Esterman. So what does the theorem say? So the theorem is actually posted here. So just as a reminder, if you don't remember what Goldbach's conjecture says, it says that for any positive even integer greater than 2, you can write it as the sum of 2 prime numbers. And then what Esterman showed is that it works for almost every positive even integer, more or less. So what's the statement say? He says, let Qn denote the number of those even positive integers less than n which are not representable as sums of 2 primes. As n tends toward infinity, Q of n, this number, behaves asymptotically like n divided by log n raised to the a power. So I've written it over here in the way that he worded it in the paper, or in the test that he gave us. And this works for any positive number a. So as a gets huge and as n gets huge, the denominator overpowers the numerator. So it more or less behaves like 0, but not quite. And this is the theorem that he showed in 1937. And this paper that I printed out is about 4 pages. So what I'm essentially going to do is read through all of this and fill in any missing details from the proof that essentially the instructor gave us, to make sure that I don't completely botch this layup that he's given us that I'm very grateful for. So I'll get this done over the weekend or maybe Friday, because I take the test tomorrow early in the morning, the probability test, and then I'll spend the rest of the day making sure that this is perfect before I turn it into his mailbox or something. So that's the kind of sort of Goldbach conjecture. The almost Goldbach conjecture, we'll put it that way. And then what about the geometry test? So the geometry test is, again, it's one problem and it's a famous theorem. It's the Confucian theorem, but he wants us to recreate the proof given by Herglotz. Because apparently Herglotz came up with a proof that was a lot simpler than the one that was originally given by Confucian. And we asked him about references of where to like learn about it, or maybe like what we really wanted to say, what book is this in, so we can go look it up. And he's like, well, there is this book by so-and-so that essentially does it. And he's like, do you want it? And I'm like, yeah, we definitely want the book. So I'm going to look up this book over the weekend and essentially do the test then. Now, instead of showing you the actual final that he gave us, there's too much information on it. So I've decided to recreate the statement here. So this is Confucian. What does the theorem say? It says that if you have a convex body K with a C2 surface, meaning that it's continuous on the boundary and it's twice differentiable. If you have an isometry, which is a distance preserving map from one to the other, or between two convex bodies. So we have another convex body over here, L, with also C2 surface, and you have an isometry from one to the other, which means that if I have a squibble or a scribble on the surface of K, then if I pass it through the isometry, the length of this scribble is the same as it is on the surface of L. That's all what really an isometry says. So the theorem says that if you have this condition, then you know L is just a rigid motion of K. And a rigid motion is essentially a rotation, a reflection, or a translation. I believe that's all possible rigid motions. I don't think there are really any others. You have K, you can rotate it, you can reflect it like this, and then you can move it around. That's more or less what a rigid motion is. And Herglotz gave a famous proof of this that was very short. It was kind of hard to find on the internet, but a friend of mine found a paper about it and emailed it to me. So I'm going to read through the paper and see if I can understand it, and then more or less give a proof of the theorem to my instructor. Here's the thing though, the instructor gave us the test as like a sequence of steps. So step 1, he says, in order to prove this, you first need to do this. And then problem 2 is, okay, now do this. And then problem 3 is, okay, now do this. And then you get to problem 9, he says, okay, now wrap it all together and you've basically done the problem, done the theorem. So you can see what kinds of final exams you can expect from these special topics courses that we take in pure math. The instructor really just wants us to understand the material and not worry too much about, giving us a test like you would at the undergrad level. Because at this point, when you're a graduate student, you're kind of more like an employee more than a student. You're there because you want to do research. So it's like, okay, you're PhD students. You're obviously good students. I don't want to give you a not A in the course. But as long as you put in the work, like you actually sit down and write the thing, that's what I think they care about most. They're just checking to make sure you're not lazy. So for that, I'm very grateful. But, at the end of the day, you have to do research, and that's much harder than studying for a test and not failing it, in my opinion. But anyway, this has been my life for the last 2 years. And I got to get these tests submitted over the weekend because I have to give my students their final exam on Monday. And I wrote I don't want to say it's an easy test, but I definitely didn't ask them anything that was weird. That was, abstract. So hopefully they'll do well on it. Anyway, I've rambled on long enough. Thanks for watching.